So let's have a little bell work for assignment. Now, what is this assignment number? Good question. It's assignment 19. And this is yet another integration techniques called by parts. Okay? We'll get to that in a minute. First, though, a little bell work. Can you evaluate this? Oh, okay. Yeah. Here's your given. X dx equals k. It is known that this integral equals k, some number. Now they give me this. They say 1 to 2 of x e to the sine 4 minus x squared dx. And they want to know what this is equal to. No, really they do. They want to know what this is equal to. So, don't run away, but think about it. You've learned a lot of integration techniques, and you should see one of them right now. If you don't, you haven't been practicing enough, and really start doing some practice problems and checking your answers. Okay, so u equals 4 minus x squared. du equals negative 2x dx. Well, I have an x dx, but not the negative 2. So I'm going to push that to the other side. So where I see x dx, I can replace that with d over negative 2. And e to the sine of 4 minus x squared, well, I can replace that 4 minus x squared with u. So this integral becomes e to the sine u times du over negative 2. Okay. Well, where do we go from here? Well, take a look. When we have e to the sine x dx, e to the sine u du, we know something about that. Well, let's take this a little further. I'm going to pull out that constant. And so now I'm looking at this. And I don't have any bounds here. And I've been saying, you can leave no bounds on your u integral. But if we do that here, it's actually going to be really problematic. So let's find our u bounds for our u integral. Okay? The way we find those u bounds is to take these x bounds and plug them into x and find out what u turns out to be. So 1 squared is 1, 4 minus 1 is 3. So that's 3. And if I plug a 2 in here, 2 squared is 4, 4 minus 4 is 0. Well, I generally like the smaller number on the bottom and the bigger one there, and I can flip those bounds provided I pull out another negative. So negative times negative is positive, and this becomes a 3, and this becomes a 0. And now look at what you're looking at. These are the same. What does this integral equal? K. So my answer then is 1/2 k. I know. I do. So here's the thing. They gave me this for a reason, and it wasn't to ignore it. It was so that when I did my u sub on this problem, I could eventually get myself to something that looked remarkably like that. And so take heart if you don't get to the place where it looks like that helping equation is going to go in. Yeah, you probably made a mistake somewhere. But this is u sub, and I want to talk today about by parts. All right. Now, just like u sub is something I do when I see a function and its or part of its derivative. I do integration by parts when I see a function and someone else's derivative. Yeah. So if I see something like the integral of x cosine x dx, of course I ask first, hey, do I recognize you? Are you an integral that I know? And the answer is, yeah, no, I don't recognize you. Do I see a function and its own derivative? No. Do I see a function and someone else's derivative? Or do I see a function and someone else's derivative? Sure, I got that. So this is biparts. Now, what's the recipe for biparts? Okay, so let's go through this gently and carefully. If I have u times v, okay, if I have u times v, and I take the derivative of this, let's take the derivative of this. This is going to, and these are both functions of x. U and v are functions of x. So when I take the derivative here, this is a product. I'm going to use product rule. This times the derivative of that. dv dx plus this times the derivative of that with respect to x. Okay, and that equals me taking the derivative with respect to x of u times v. Great. So where does that bring us? Well, I kind of want to take the integral of both sides. I know, why would I do that? So there I am, integrating all these bits. Okay. Integral, derivative, they undo each other. So I've got just u times v over here. dv dx, well, you might be more comfortable calling that v prime. Plus integral of v u prime equals u v. Now, what I'm looking for is a function and someone else's derivative. And what is that equal to? Well, let's get this all by itself by subtracting the integral of v u prime from both sides. So we're going to have then the integral u times v prime is equal to u times v minus the integral v times u prime. Okay, so many former students have told me the U of A expects you to do this. Not that you have to do this for the grade, but this is what's presented as your method of finding the antiderivative when you're looking at a function and someone else's derivative. I actually want to show you something here, right? I want to see this in a different way. And my different way is going to come in the form of a graphic organizer. And my graphic organizer is going to be u, v, du, and dv. So I'm putting a function here and the derivative of someone else's function here. So for example, in this problem, we were just looking at x cosine x dx. I'm going to put my x here, and I'm going to put my cosine x here. I'm understanding that this is the function, and this is the derivative of someone else's function. Okay? Yes, we'll talk about what happens if you switch them and put the cosine x here and the x here. I promise we'll talk about that next. So what do we do with this little graphic organizer? Well, going this way, I take the derivative, and I have 1 dx. And going this way, I do the antiderivative. Whose derivative is cosine? Sine's. Okay? Now, once you've filled this graphic organizer out, remember what our recipe was. We said that the integral of u v prime was going to be u times v minus the integral of v u prime. So let's do this here. U times v, that's multiplying these together, minus the integral of v u prime. U prime is 1 dx. The antiderivative of negative sine, well, that's going to be positive cosine. And don't forget the plus c. So, deriving the by parts, coming up with this, and then doing this is what many students have told me that their calculus instructor in college wanted them to do. And it's only because they don't know how to do this. And you do. What did we just do? We did u times v minus v times u prime. What do I know about v times u prime? V u prime. So, this times this minus the integral of this times this. Again, this times this minus the integral of this times this. That's by parts. So, what is it that we're undoing here with by parts? Well, remember, our initial question was, what do I do when I see a function and someone else's derivative? And the answer is, this is the integration technique that I'm using, not to undo chain rule, that's a u sub, but instead to undo product rule. What I'm doing here is undoing a derivative with product rule. This is the result of using product rule. If I want to undo this, I use by parts. And I definitely use this recipe, tied to this graphic organizer. U, the function, goes here. The derivative of someone else's function goes here. Derivative on top, antiderivative on the bottom. My recipe is this times this, minus the integral of this times this. Okay? Now, let's go back to this. What happens if I put things in differently? Well, let's see. I take the derivative going this way, and I do the antiderivative here. And I follow my recipe, this times that. So I've got x squared over 2 cosine x minus the integral of, I'm going to take that negative and put it here and then move it there. So that's going to be a plus x squared over 2 sine x dx. Now, compare where we are now with where we were. This is a more complex expression than this. I'm going in the wrong direction. If what's here is more complicated than what's here, you're moving in the wrong direction, and it probably means that you guessed wrong, and you should flip these two. Instead of putting the trig thing as the thing you take the derivative of, put the polynomial there. It's almost always the polynomial there because the polynomial, when we take the derivative, will get a lot simpler. And cosine x, and we're okay going backwards with cosine x. So again, this times this, minus the integral of this times that, and so we get x sine x minus negative cosine x plus c. And that minus a minus, I would probably make it plus cosine x plus c. If you take the derivative of this and enjoy the product rule, we'll simplify back to this. Okay? So that's by parts. Guess what? It's your turn now. Let's take a look at by parts. You should do these. integral x e to the minus x dx. Pause the video, give it a try. So I've got a function and someone else's derivative. Or I have a function and someone else's derivative. Again, I'm going to put the polynomial here and e to the minus x down here. Okay, dx. So what goes here is the derivative of this. What goes here is the antiderivative of this. Okay, so that's negative e to the minus x. You might want to check that. If you take the derivative of this, e to the is e to the times the derivative of the inside. That's going to be negative 1 times this negative. That makes that positive. Great. Now, what's our recipe here? Well, our recipe is this times this, negative x e to the minus x, minus the integral of this times this, negative e to the minus x dx. I'm going to pull that out, so I'm going to have negative x e to the minus x plus the integral e to the minus x dx. And the antiderivative of e to the minus x dx is e to the minus x, but don't forget there has to be a negative in front. Why? Well, the derivative of e to the minus x is e to the minus x times the derivative of the inside. I don't see a minus here. So there must have been something present in your original function, so that when I took the derivative and that extra negative showed up, negative times negative gave me that positive. All right, and then here we have negative x e to the minus x, and don't forget the plus c. Yes, you could factor out an e to the minus x. In fact, you could factor in negative e to the minus x out here. And that may be actually something to do, but I can't do it here. So I would have to write this as negative e to the minus x, x plus 1 equals, plus c. That's my tidier form. Yeah, I wonder if we'll be setting integrals equal to 0. Okay, how about this one? The integral of ln of x dx. The integral of ln of x dx. So, yeah, no, really, you actually do see a function and someone else's derivative. I see a function. Do you see its derivative? Do you see 1 over x anywhere? No, not me. And some other functions. So I put ln of x and 1. The derivative going this way, 1 over x dx. The antiderivative going this way, x. So finish this out. Take a moment to finish this out. And I look forward to seeing how that goes for you. Did you do our recipe? X ln of x minus the integral x times 1 over x dx. Well, those cancel, and I've got x ln of x minus the integral of 1 dx. And that's going to be x ln x minus x plus c. Okay, there's our antiderivative of ln of x. No, I don't think you should memorize that. But I do think you should, be able to do by parts. Sorry, you're right there. So, how about this? The integral of x squared e to the x dx. Okay, I see a function. I see someone else's derivative. In general, almost always, put the polynomial here. And the other function there. So I want the antiderivative this way, and I want the derivative that way. So what's our recipe? This times this, x squared e to the x minus the integral of this times this. 2x e to the x dx. Hey, do you recognize that? No, me neither. Guess what? I see a function and someone else's derivative. Yep, I got to do by parts again. So, look, if you started with a polynomial here, you got to keep going with the polynomial here. If, in fact, you put the polynomial down here, this 2x, and you do the antiderivative, you're actually going to end up back where you started. So, please, stay consistent. 2x, 2tx, e to the x dx is e to the x. This times this. Wait a second. All of this, by parts that I'm about to do, is behind this minus sign. So let's respect that minus sign with some brackets. This times this, 2x e to the x minus the integral of 2 e to the x dx. This times this, minus the integral of this times this. Well, that's great, because there's a constant, and there's e to the x. And so I know I'm going to have x squared e to the x minus 2x e to the x minus a minus plus 2 e to the x, and don't forget the plus c. Ta-da! There it is. Look, we had to do by parts twice. And yeah, that's a thing. And yeah, don't be surprised. So, what do you think is going to happen when we integrate x to the third e to the x dx? Good question. Well, give it a try. I mean, clearly I see a function in someone else's derivative. This is not a u-sub, and I don't recognize that derivative. And no, I'm not going to do a differential equation here. So, what's it going to look like? Well, again, I like putting the thing that gets smaller and less complicated as the function, and anything else as the derivative. Take the derivative on top, and antiderivative on the bottom. So this integral becomes this times this, x to the third e to the x minus the integral of this times this, 3x squared e to the x dx. Hey, look! I've got a function times the derivative of some other function. Let's use by parts again. 3x squared is going to be 6x dx, and down here I have e to the x, and I go backwards and I have e to the x. Remember, all of this by parts is behind that minus sign. So now I'm going to have x to the third e to the x minus 3x squared e to the x minus the integral of 6x e to the x dx. Okay, so what about that? By parts a third time. 6x, 6 dx, e to the x, e to the x. And so remember that all of this is behind that minus sign. And we haven't even distributed here. So maybe we should do that distribute. Let's distribute that negative. Negative times negative makes positive. Okay, and now this one with this by parts. So we've got x to the third e to the x minus 3x squared e to the x plus 6x e to the x minus the integral of 6 e to the x dx. And the antiderivative of this, no problem. 3x squared e to the x plus 6x e to the x minus 6 e to the x plus c. 1, don't forget the plus c. 2, I can pull that constant out and say, what's the antiderivative of e to the x? It's e to the x times that negative 6 that was out in front. By parts 3 times. Well, look, so yes, we can do this, but there seems to be some kind of a pattern here. And so I would like to introduce you to my time and labor-saving friend, tabular. Curiously, I've had a lot of students contact me and say that their college or university calculus teacher didn't teach them tabular either. Yeah, you really want to use tabular on that last problem. So here's how tabular works. We're trying to do this problem, x to the third e to the x dx. We make a table. We put function on this side and derivative on this side. And over here, we take derivatives. And over here, we find antiderivatives. So my derivatives, 3x squared, 6x, 6, 0. And over here, antiderivative, very convenient, very easy for us. And here's how it goes. It does not go across. It goes this way. And so we've got equals x to the third e to the x plus 3x squared e to the x plus 6x e to the x plus 6 e to the x. Don't forget the plus c. But there's a problem. This isn't exactly what we had when we did by parts 3 times. And that's because there's a little bit of something else happening, which is when I go backwards, we saw with that formula, remember, minus the integral v times u prime. There's that minus every time we go back. And that has to show up here in the table. And the way it shows up is we multiply this by a positive. We multiply this by a negative. We multiply this by a positive. We multiply that by a negative. Yes, the signs always flip. And no, it is not make this term be positive, make that term be negative. It's literally multiply this times a positive. Sign stays the same. Multiply this by a negative. Ooh. Multiply this by a positive. Doesn't change. Multiply this by a negative. Now, this is a fairly easy, straightforward problem. If we had had something like minus 2x, be careful with that. I mean, be careful with that whether you're doing it by parts 3 times or you're doing it as with tabular here. Okay, so let's take another tabular look at this problem. Okay, this problem. Still have to take derivatives on one side and antiderivatives on the other. And some students have difficulty with this, so we need to think about this. This, no problem, you're all really comfortable. 6, 0. Okay, I know, stop. There's nothing else to take the derivative of. Now, over here, okay, so over here, I'm doing antiderivatives. So, if I take the derivative of this, do I get that? Because if I take the derivative of this, I do get e to the minus 2x times the derivative of the inside, negative 2. But I don't see a negative 2 out in front here, which must have meant that the original function had something so that when I took the derivative, that inside negative 2 would cancel away. So here, e to the minus 2x over minus 2. And of course, you could write that as negative 1/2 e to the minus 2x. Now, when I go backwards again, that same thing is going to happen. I'm going to need another negative 2. And so I'm going to have, here, I'm going to say e to the minus 2x with the negative 1/2. No, that. Let's imagine that this is my antiderivative, and I bring down that negative 2. But I see a negative 1/2 here. So when that negative 2 comes down, there must be something present in the original verb, so that I get the canceling and I get the coefficient that I'm looking for. So we're going to have e to the minus 2x over 4. If I bring down that negative 2, negative 1/2, yes. and e to the minus 2x over negative 8. You don't believe me? Well, take the derivative here. The derivative of e to the stuff is e to the stuff times the derivative of that inside function. Don't forget, times that constant, negative 1 over 8. So negative times negative makes positive, and 2 and 8 simplify to positive 1/4 e to the minus 2x, and there it is, 1/4 e to the minus 2x. So here's what I'd like to tell you. This dividing by negative 2 happened each time. Another negative 2 times negative 2 is this times negative 2 is this, and now I'm ready to use my tabulator. So that one, that one, that one, oh gosh, I need another one. So this is going to be e to the minus 2x over positive 16. And now, don't forget the signs. I'm going to multiply this expression by a positive, and this expression by a negative, and this expression by a positive, and this expression by a negative. So what's my integral look like? Don't lose that minus 2. Negative times positive is negative, so I'm going to have negative x to the third e to the minus 2x all over 2. And then I have, it's positive 4, then I have this times this, and I multiply this times this by that minus, and I get minus 3x squared over 4 e to the minus 2x. And now I'm down here, and I have a minus times a plus, and yes, I can take a 2 out of each of those. So a minus times a plus is a minus 3/4 e to the minus 2x, and there was an x there as well. Okay, so let's put that in. And then finally, here, I'm going to multiply by a negative this. Oh, look, 6 and 16 I can reduce there. That's going to be 3 over 8. So I'm going to have minus 3 over 8 e to the minus 2x, and don't forget the plus c. So, like some students say, the sign should alternate plus, minus, but look, they didn't. They're minus, 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 minus. So, no, it is not this is the sign. It is multiply what you've got times a positive. Multiply these two things by a negative. Multiply these things by a positive, and multiply these things by a negative. Okay, so there's tabular. And I think it's time now for you to practice 1 or 2 of these. So, will you please do this one? The integral of would you please find t squared e to the 5t dt? Okay, please, please, please. And I encourage you to use tabular, but you could do by parts a bunch of times if you prefer. Pause the video, give it a try. Hey, welcome back. So, t squared, 2t to 0, and here, e to the 5t, e to the 5t over 5, e to the 5t over 25, and e to the 5t over 125. I've got to divide by another 5 each time I go back, because this 5t is always there. Every time I take that derivative, I gotta, have an extra 5 on the bottom to cancel with that 5 that comes out from taking the derivative of the inside part. I mean, let's look. We've got 1 over 125 times e to the 5x. So if I take the derivative of e to the 5x, that's going to be 5 e to the 5x times this constant. And lo and behold, I've got some canceling. And look, there it is. So really, every time I go back, I got to multiply by another 5, or multiply by the derivative of that inside function every time I go back. Okay? On the diagonal, we've got t squared over 5 e to the 5t. We've got 2t e to the 5t over 25. We've got 2 e to the 5t over 125. Don't forget to multiply this by plus, this by minus, this by plus. So if I multiply this by positive, it stays positive. If I multiply this times a negative, I got a minus there. This times a positive is a positive with that, and don't forget the plus c. All right? And you know, if you're unsure, you could always take the derivative of this. If you take the derivative of this, you should end up there. All right, how about this one? What can you do with this one? The integral of y ln of y dy. Yeah, I'm not using tabular for this. I'm just going to do by parts. But careful, because a lot of students want to put the polynomial here, and then they run into this situation. Do you remember the antiderivative of ln of y? No, you probably don't. You know how to do the derivative of ln of y, so we're going to go this way. The derivative of ln of y is 1 over y dy. The antiderivative is y squared over 2. And I agree. I did say that got more complicated. Do I really want to do that? Well, let's take a look. This times this. So we've got y squared over 2 ln of y minus the integral of this times this. Well, look what happens. One of these cancels with that. I can pull the constant out. So let's take that one out. And now I'm just integrating of y dy. Yeah, that's a gentle integral. So, yeah, the only thing that's superseding me putting a polynomial up here is I'm not comfortable with the antiderivative of ln. Okay, let's finish this up. This is going to be y squared over 2 ln of y minus the antiderivative of y is y squared over 2 times that. So I'm going to add minus 1/4 y squared, and don't forget the plus c. So that is my, let's see, what is that? There's one negative there. Oh, that's not. Here we go. So there's my antiderivative. We did do the derivative, the antiderivative of ln of x, but really I don't recommend you memorize that one. I do think it would be good to do one more tabular, and I'm looking for a convenient tabular, and I'm finding one that I was expected to. It's a great set of problems there. Oh my goodness. So let's. Oh yeah, how about this one? Here we go. The integral of x squared cosine 4x dx. I'm going to give this one a try. I recommend tab. Okay, welcome back. Tabular, x squared, 2x, 2, 0. Antiderivatives. Well, the cosine for x goes here. The antiderivative of cosine, the antiderivative of cosine is sine. But if I take the derivative of this, I'll get to taking the derivative of the inside, which will be 4, and I don't see a 4 out here. So there must be something present on the original function, so that when I do take the derivative of the inside, and that 4 does come out, It has a 4 to cancel with because I have no 4s there. And this is going to happen every time I go backwards. I'm going to need another 4 on the bottom. So what's the antiderivative of sine? It's going to be negative cosine 4x over now 16 because I needed another 4. And when I go again, the antiderivative of negative cosine is negative sine, and I need another 4. Going on the diagonal, don't forget, we're going to multiply this one by positive, this one by negative, this one by positive. So we should end up with x squared over 4 sine 4x, positive times this stuff. Now we have negative times negative. It's going to be positive. 2x over 16 is x over 8 cosine 4x. And now I've got a positive times a negative. And that's going to be 2 over 64. So I have negative 1 over 32 sine 4x. Don't forget the plus c. Okay, 1, 2, 3. Yes. Minus times plus is minus. Minus times minus is plus. Positive times positive is positive. There we go. All right, well, I hope you're feeling a little more comfortable with tabular. Here, this is the biggest thing that students get wrong on the test. They forget to do this, or they do some sort of misremembered thing where instead of dividing by 4, they're multiplying by 4s. And, you know, I recommend take that derivative just to confirm. So here's the next one let's talk about. Yeah, what about this one? What's going to happen here? What if we have the integral of e to the x cosine x dx? I see a function and someone else's derivative, or a function and someone else's derivative. That's by parts. Tabular? Well, wait a second. Isn't this, like, if I choose this for my derivative, it never goes away. And if I choose this for my antiderivative, it also never goes away. This is a problem. And if I put them in the, you know, if I flip them and say, all right, well, let's make this one the derivative. So we have negative sine x, cosine x, sine x. We have derivative of sine is cosine x. And over here, we just have a bunch of e to the x's, and really no one's giving way. And so what is it that I'm supposed to do? Well, yeah, don't do tabular. Do by parts. And it doesn't matter which of them you put in which of these. I would say use whichever one makes your life less full of stress. And for me, I would much prefer to take derivatives of trig functions than antiderivatives. My little dyslexic brain often makes sign mistakes going backwards with trig functions. So I'm going to take the derivative up here and get negative sine x, and I'm going to do the antiderivative here, which is e to the x. So our recipe, integral e to the x cosine x dx, is equal to e to the x cosine x minus the integral of this times this, minus e to the x sine x dx. And yeah, I'm going to pull that negative out and turn that into a positive. Okay, but yeah, I agree. Mr. Koopa is not any better. So do it again. No, really. And because you started triggy up here, you need to keep going triggy. If you don't, if you now say, let's put the e there, you're going to go back to the original problem. So don't do that. Instead, put your triggy thing here, and put your not tricky thing here, only because that's the way you did it there. Yes. So now, behind this plus sign, we have this times this, integral e to the x cosine x dx minus equals e to the x cosine x plus this times this, e to the x sine x, minus the integral of this times this. So that's going to be minus the integral dx. Good. And I agree. This still looks the same. But wait. But wait. Isn't this and this the same? Right? Aren't you trying to say what that's equal to? So, stop. By parts twice, stop. And notice, you must have a minus here. If you don't have a minus here, you made a mistake. Go back and find it. This must be a minus when you're done with the second by parts. Because what I'm going to do now is add integral e to the x cosine x dx to both sides. Because over here, these cancel. And over here, one of them plus one more of them gives me two of them. Now, how does this help? Oh, and I'm going to factor out an e to the x there. Cosine x plus sine x. And yes, there is a plus c. But I'm going to hold off on that a second because I don't want to know what 2 times that integral is equal to. I want to know what that integral is equal to. So I need to divide by 2. Let's see. Ta-da! So, if both of them are going to spin forever, what you need to do is go around twice. You should get back to your original when you've gone around twice. There should be a minus in front of it when you go around twice, and you should add that quantity to both sides. Now, that being said, sometimes this is something like, I don't know, 4/3 times the integral. And so you're adding 4/3. And so you're adding 4/3. And so 3/3 plus 4/3, you'd have 7/3. And so you multiply both sides by 3/7. Okay? So that can happen here too. So I think you need to do one of these. Okay? Or, oh my goodness, that's all our problems for today. Well, I think you're fabulous, and I can't wait to look at some more tabular stuff with you. Then we'll spend a day doing partial fraction decomposition if we have time, and then it'll be time to review for our unit test. All right, see you in the next video. Have a great day, everyone.